All right, so let's go ahead and talk about the 2021 FRQs. These are obviously from the first administration date. These are not going to be the same FRQs that you guys are going to see. But I think this is definitely beneficial to kind of check out, as these are the most recent questions that they have released. So students that were in AP Calculus BC this year that have already taken the exam. Now, on the teacher forums, they've said, well, my BC students said that they took the exam, but they didn't have these questions, or they had only some of these questions. So what they're doing is they're not giving every student the same questions. So they're kind of having different versions of the test is what it seems like. And but anyway, these are the ones that were released. So that's what we're going to be talking about. And I asked you guys to focus on these over the weekend. So here we go. Table of values. Oh, let me also say, so in my Google Classroom, for calculus, I put up a bunch of stuff about in my stream. So what I said was 1 week from today, right? Figure out what you need to focus on out of these BC concepts. So Taylor series, polar, parametric, techniques of integration, differential equations and logistics, convergence tests. And then there's working with tables that's there. Working with tables is not a BC only concept, right? But that's definitely one. And then putting it all together. Again, these aren't the only concepts that we're expecting on the AP exam. These are just the BC only concepts, except for, of course, working with tables. But within this working with tables one, which should be up here, working with tables, this has a nice little review where they give you some questions, and then they ask you about to do certain things, and then I also give the solutions there so you can go through. Now, so let's go back to, and then Ask Mr. Calculus. If you just search for Ask Mr. Calculus and go do his 2021 FRQs, he has the solutions already there worked out. So here we go for BC1, right? We have a table of values. You should expect one problem with the table of values, okay? As we're looking at the past, FRQs and what we have seen, table of values is very, very common. In fact, I would say you're looking at, they're going to give you one of them, either the table of values, or they'll give you the function, or they will give you the graph of the function. So I'm looking at those, and at least one of them will be the original function, and then at least one of those will be like the derivative of the function. So this is r prime of t, find r of whatever. So that's what we got going on. So for this, it says the density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f, where r is measured in milligrams per square centimeter. Values of f of r, again, f of r is just the density, and it's based on the radius from the center, right? Are given in the table above. Use the data in the table to estimate f prime of 2.25. Well, they give us f of 2 and f of 2.5. So to find an estimate for f of 2.25, you have to find the average value. So remember, f prime means the instantaneous rate of change. Well, we don't know what that is at exactly 2.25. So we can find the average rate of change in between 2 and 2.5. So that would be f of 2.5 minus f of 2 divided by 2.5 minus 2. So that's going to be 10 minus 6, which is 4, divided by 0.5 or divided by 2.5 minus 2, which is 0.5. So 4 divided by 0.5 ends up being 8. okay? So, using correct units, interpret the meaning of your answer in the context of this problem. Well, if F is the bacteria population and R is the distance away from the center that we're going out, or the radius from the center. So F prime of 2.25 means, so using correct units. So that's going to be the rate that F is changing as R changes, right? So the rate that F is changing as R changes. So that's going to be milligrams per square centimeter per centimeter. So let's look at the rate that F changes as R changes is really what it is. So what is F? F is in milligrams per square centimeter. So it's milligrams per square centimeter per R changing. Well, R is centimeters. So let's see what this guy says. For this, the density of a bacteria population in a circular petri dish at a distance of 2.25 centimeters from the center of the dish is increasing at a rate of 8, and that's milligrams per square centimeters per centimeters. So that would be the unit for this. All right. I feel like you guys are not with me. Are you guys with me? You ready to go? Okay. Now let's go back to this. So we were given a table of values and we were asked to approximate or estimate F prime of 2.25. Just as easily, they could have asked us to approximate F of 0.5, or sorry, F prime of 0.5 or F prime of 1.5 or F prime of whatever halfway between 2.5 and 4 is. What would that be? 3.25. So they could have said approximate F prime of 3.25, right? It's the same concept. So then it says the total mass in milligrams of bacteria in the petri dish is given by the integral expression 2 pi times the integral from 0 to 4 of R times F of R dr. Approximate the value of that using a right-Riemann sum with 4 subintervals. Okay, so let me go ahead and take a picture of this, and then I'll work this guy out for you. Okay. So here's what we have. We're using a right Riemann sum with 4 subintervals. 1, 2, 3, 4, and we're using a right. So it's going to be, we're going to use this value and use this value. So for the first, second, third, and fourth. But here's what we got. It's not just the integral of F of R. What we're going to have is, so 2 pi times the integral from 0 to 4 of R times F of R dr is approximately equal to, so I'm going to keep that 2 pi out in front. So this out in front is going to be right there. And then for this integral, I'm going to put that. And again, this is going to be an approximation. So what I'm going to say is R times F of R. So times dr, right? So there are 3 things that are going to go into each one. It's going to be R. So for this first set of points, it's going to be the R value times F of R, which is 2 because I'm using the right-hand point, times dr. Remember, dr, that's like your delta R. So on that first one, what is my delta R? The change in R values of that first little cloud that I just have. Just 1, because I'm going from 0 to 1. Plus, so now let me use green for the second guy. So my second subinterval is this. So now it's R. Well, the right R is going to be 2 times f of R, which is 6, times the change in R. Well, what's the change in R going from 1 to 2? 1 plus, so let's go with my third cloud, which is really going to be, represent a rectangle. And I could, plot these points on, the axes and then talk about it that way, which maybe I'll do that after. But here we go. This is now going to be the R value, which is 2.5, times f of R, which is 10, times delta R. What's delta R now? It's not just 1, is it? 0.5 plus excuse me. So I'm going to choose another color. Let's go like this, pink. For these two guys right here, that's going to be 4 times 18 times, what's my delta R for that guy? 1.5. So whatever I get by doing this, so this guy ends up being 18 times 1.5 is 9 times 3, 27 times 4, 27 times 4, 104. Maybe I don't know, I'm doing this kind of quickly, but here we go. 5 times 12.5. This guy's going to be 12. And this guy's going to be 2. So let me see when I add that. 116, 128, 130.5. Is that right? 130.5. So that'd be 261 pi, something like that. I don't know if I did that right. Let's check. Let me see. I don't know. Again, I'm just doing this. You got 269 pi. I don't know what I got. What did I get? 261 pi. Let's see what he has. He has 1 times 2 times 1, 2 times 6 times 1, 2.5 times 10 times 0.5, and 4 times 18 times 1.5. So did I make a mistake here? 18 divided by 2.
That equals 108, I think.
108 right here.
Mm-hmm.
Mistake. This one is 108 right there, Lauren. So adding 4 there. And then that'd be 134.5 and then 269. There you go, 269 pi. So that's that. Sorry, I'm trying to go quickly by doing this stuff in my head, but that's what we have going on for that right now. It says approximate that value using a right Riemann sum with the 4 subintervals indicated by the data in the table. I want to point this out. Most of the time, you are asked to find a problem using a Riemann sum in like the calculus book. We have equally lengthed subintervals, so our delta x we could bring out front. Here, and most of the time on the AP exam, the subintervals are not equally lengthed. In fact, the change in R for this was 1, 1.5, 1.5, right? So they were not equally spaced out, equally lengthed subintervals. So we had to deal with those. And then those, delta R's were there, 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 and there, right? So that's what we have going on. Okay. So that was part B. Let's now go back to this guy and say part C. Is the approximation found in part B an overestimate or underestimate of the total mass of bacteria in the Petri dish? Explain your reasoning. So let's go back up and read the problem. Oh, I have that f is an increasing function, and we used a right-hand approximation. If f is an increasing function and we use a right-hand approximation, is that going to be an over approximation or an under approximation? Over approximation, right? Let's see what they say. The approximation found in part B is an overestimate because f of r is an increasing function, so r times f of r is an increasing function. Okay, maybe you have to add that, okay, because f of r is increasing, and in the, the integrand is r times f of r, but r is positive also, so therefore you're going to have an increasing function. Well, positive and greater than 1, I guess. Okay, next. Part D, the density of bacteria in the Petri dish in between 1 and 4 is modeled by the function g. So now the density, we had specific values given here in this table, but now they're saying, hey, we have modeled it by using g of r. So this is g of r. For what value of k in between 1 and 4 is g of k equal to the average value of g of r? This is average value of a function, yeah. Yeah. So what is average value of g? The average value of g, so let's just go to this, right? So we answered C already. So let's just go to D, and let's talk about average value of D. Average value of g of r is known as g av, which is 1 over b minus a times the integral from a to b of g of r dr. Right? So find, we're looking for the value of k where g is equal to its average value. So let's first find the average value. So for this, g av equals 1 over, and again, this is from 1 to 4. So 4 minus 1 times the integral from 1 to 4 of g of r dr. Well, they give that to you, so you just plug that into your calculator. Yes, this is a calculator problem because it's problem 1. Problems 1 and 2 on the first response are going to be calculator questions. So I'm going to go and just see what Mr. Calculus got because he worked it out, I'm sure, and got 9.875794868. So once I work that out and get that on my calculator, I'm then going to store that as alpha A, right? Store that as alpha A, which he has equals A right here. And then you're going to set that G equal to that value. So G of K is equal to 9.875 whatever, and then you're going to find, so how would you do that in your calculator? How would you do that? You guys talk to me. How would you find where the function is equal to one specific value? Graph what though?
The function minus a.
Exactly. So what you would do is you would graph the function minus a into y sub 1 and then see where that hits the x-axis. Or the other way you could do it is you could graph the function in y1. So graph g in y1, graph a in y2 and see where they intersect. If this is the function and this is the line, they're going to, or this is going to be the horizontal line. So it's going to go boom. And wherever they intersect, that x value is going to be the k value. And you know that it's going to only occur between 1 and 4 because that's the interval that they give us. So they found that to be about 2.497. Okay, so that's problem number 1. Cool. That was just a table of values. Here we go for problem 2. Here we go. This kind of reminds us, oh yeah, we had that whole polar, parametric, and vector unit. So let's talk about that. For time t greater than or equal to 0, a particle moves in the xy plane with position x of t, y of t, and velocity vector given. So this is the velocity vector. They also give us the initial position, meaning at time t equals 0, the position is -2, 5. Find the speed of the particle at time t equals 1.2. And then find the acceleration vector at time t equals 1.2. What do we do to find speed? Blake, were you asking a question?
No, sorry, I was stretching.
Okay, so speed. For vectors, what did we do to find speed?
Square root of something.
It's the square root of x prime of t squared plus y prime of t squared. Okay? So that's, let me go ahead and so this is going to be 2a. We have speed is the square root of x prime of t squared plus y prime of t squared. So this is x prime of t because they say that that's the velocity vector. And this right here is y prime of t. So you're going to find, I mean, this is just plugging into your calculator. Find x prime of 1.2 and find y prime of 1.2. Square each of those separately and then add them together and then take the square root of that. Because that's the formula for speed. So at t equals 1.2, that gives us the square root of x prime of 1.2 squared plus y prime of 1.2 squared. And then whatever that ends up being. We'll come back to that, or I'll show you the solution for that later. Part B asks us to find the total distance traveled. What is total distance traveled when we talk about parametric, curves or parametric equations?
Arc length.
It's just the arc length for that. So in this case, so it says on the interval from 0 to 1.2. So the arc length, so I guess I should put it like this, right? Total distance traveled equals arc length. So total distance traveled equals L equals the integral, let's say from 0 to 1.2 of what? What is it for parametric?
Square root.
It's
of-
the same thing as what we have there, right? But x prime of t is given to us up there, so this is going to be t minus 1 times e to the t squared plus, and then y prime of t is sine of t to the 1.25 squared, and then this is going to be dt. Okay, so that's what total distance traveled is, which is just arc length for parametric, right? And again, parametric vectors, it's all like this velocity vector is given as the, x component, really x prime component, and y, really y prime component. And so we deal with it as we did with parametric. So that's what's going on there. Okay, find the coordinates of the point at which the particle is farthest to the left for t greater than or equal to 0. So, and then there's another part of that, which is explained blah, blah, blah. But here, let's go and let's do that. So, I'm going to use maybe blue for that. So C. So farthest to the left. Okay, farthest to the left. Does that have anything to do with Y? Do I care at all about my Y component or Y prime component? No, I don't, right? Because when they're asking left and right, that's the X. Up and down is the Y. So we're going to focus on the X. Focus on the X component. Okay, now, basically what they're giving us here is that X of 0 was equal to, what did they say? When t is equal to 0, the position of the X is -2, is -2. And they're giving us that X prime of t, which I indicated up here, is t minus 1, quantity t minus 1 times e to the t squared. And that minus didn't show up, t minus 1. So how am I going to find the coordinates of the point at which the particle is farthest to the left? So let's first find the time when the particle was furthest to the left. What would I do for that? The time when the particle is furthest to the left. Okay, so the first thing I'm gonna do is I'm gonna set x prime of t equal to 0, right? So I'm gonna say x prime of t equals 0 implies, and then you could work this out however you want. I think it's easy enough to say that that's gonna be t minus 1 times e to the t squared equals 0. So t minus 1 equals 0 implies t equals 1. E to the t squared equals 0 implies never, right? So t is equal to 1. That's the only t value where x prime is equal to 0. Now let's verify. So again, I'm only on my sign chart here, I have 0. I only care about what happens when t is greater than or equal to 0 because they tell me that up here, t is greater than or equal to 0. So on my sign chart, I don't need to worry about anything to the left of 0 or when t is negative. And then I want to plug 1 in here. And then let's have my x prime of t up there, and then x of t down here. So if I plug in something in between 0 and 1, something like 1/2, do you see that e to the t squared will always be positive? And then here, t minus 1, because that's what x prime of t is, t minus 1, when t is like 1/2, 1/2 minus 1 is negative. So negative times a positive is a negative. So I have that x prime is negative, which indicates that x is decreasing there, right? And then whenever whenever t is greater than 1, that's going to be positive, that's going to be positive. So x prime will be positive and x will be increasing, right? So x is increasing from there on out. So here's what this tells me. This tells me that at t equals 1, the particle is farthest to the left. That's not the question that they asked. So if you put t equals 1, you didn't answer the question. Let's go back and see what that question was, or what they told us to find. Find the coordinates of the point at which the particle is furthest to the left. So now what I found is the particle is furthest to the left at t equals 1. What's the x value there? How could I figure that out? Well, what I would say is x of 1 equals x of 0 plus the integral from 0 to 1 of x prime of t dt. What is this, people? What is this?
The thing you say,
The thing I say. That thing.
where you are equals where you were plus how much you changed.
Exactly. Where you are is equal to where you were plus how much you've changed. The x position at t equals 1 could be found by finding the x position at t equals 0 plus how much the x position changed from 0 to 1 as t increased from 0 to 1. So I'm going to say that x of 1 is equal to x of 0. Well, what was x of 0 again? Negative 2 plus whatever that is. You know, this guy is this t minus 1 times e to the t squared dt. You plug that into your calculator. So that's negative 2 plus that, and then you're going to get the x value. What about the y value? Because I'm going to need the y value now because it doesn't say only the x value, but it says find the coordinates x comma y. So what I'm going to say is, let's choose red for x, for y. Y of 1 equals y of 0 plus the integral from 0 to 1, that's a 0, of y prime of t. Well, what's y prime of t? Sine of t to the 1.25 dt. So y of 1 equals, what was y of 0 again? Y of 0 was 5, right? So it's going to be 5 plus whatever that integral is. And I'm not doing those integrals here because that's just plugging it into your calculator. But let's go back to the solutions that Ask Mr. Calculus gave us. Here we go. This is for problem 2. Here we go. Right, so let's see what they did. So for the speed, they just plugged in 1.2 in for x prime and y prime, squared them and took the square root to get that. Oh, I don't think I found the acceleration vector. Did I? Yeah, they asked us to do that, and I only did the first part. Look at, I only did the first part here. Find the speed. And then they asked us to do this, and I didn't do that. Acceleration vector. Well, all you're looking for is, because this is, x prime and this is y prime, the acceleration vector would be x double prime of 1.2, comma, y double prime of 1.2. So all you would do is you would find the derivative of this and then plug in 1.2, which you could put into your calculator, right? Math 8 gives you the numerical derivative, Math 8 at t equals 1.2. So anyway.
Is that all the work you have to show?
Yeah. And then you have to obviously give the numerical answer for it. But yeah, that's all. Look at, that's all they have. Acceleration vector at t equals 1.2 is that, which is equal to, and they got 6.247 and 0.405 for the acceleration vector. Part B, the total distance traveled. They just plugged it in and got 1.009817, whatever. So you can either leave it as 1.009 or 1.010. You got to put 3 digits to the right of the decimal point. Don't forget about that, right? Now, you could totally leave this full thing there, this full decimal. All that they are looking for is at least 3 digits to the right of the decimal. So if you don't know, oh, how am I going to round that or should I truncate? You can write the whole thing and you'll get it right. Okay, for part C, what they say is, oh, and I didn't answer that last question about why there's no particle or no point where the particle is furthest to the right. But here we go. So for t greater than or equal to 0, the particle is farthest left on the at the minimum value of x. So x prime of t equals 0 when t is equal to 1. And they have that. So the minimum value occurs at t equals 1, and the particle is farthest to the left when t is equal to 1. The coordinate of those points are, look at this, x of 1 equals x of 0 plus the integral from 0 to 1 of x prime of t dt, which ends up being negative 2.603 or 4. Y of 1 is equal to y of 0 plus the integral from 0 to 1 of y prime of t dt, which ends up being 5.410. Okay? Now, let's answer that last question, which was like, why is there no, explain why there is no point at which the particle is farthest to the right. There's no point at which the particle is farthest to the right because x prime of t increases without bound when t is greater than or equal to 0, right? And we saw that in our work with our sign chart. Right there, right? We see that when t is greater than 1, x keeps increasing. So therefore, there's no value where the particle is farthest to the right. Okay, how you feeling so far? I know you guys hopefully looked at these on your own and attempted them, and now we're just going through them. But so I hope you're feeling pretty comfortable. Here we go. Next one. Okay, so those are the calculator free response questions. So now we're going to the non-calculator. Now, again, you will still have the first two free response questions that are calculator. They're not going to take those away. You will still have those. They'll just take away your calculator and then give you the 4 additional questions and then give another hour. Remember, there's 15 minutes per free response question. So for the 2 questions, you get 30 minutes. So that's with your calculator. Then they take your calculator away. They give you 4 additional, so that's an extra hour. You can go back and answer more parts of the calculator free response questions if you need to. Okay, so here we go. End of part A. Part B. Look at this. 1 hour, 4 questions, no calculator allowed. So here we go. A company designs spinning toys using the family of functions of y equals c times x times root 4 minus x squared, where c is a positive constant. The figure above shows the region in the first quadrant bounded by the x-axis and the graph of that for some c. Each spinning toy is in the shape of the solid generated when such a region is revolved about the x-axis. Both x and y are measured in inches. So they make these toys, these little spinning toys, and they look like this. Find the area of the region in the first quadrant bounded by the x-axis and the graph of that when c is equal to 6. Find that area of the region. Okay? So what do? You tell me, talk to me, or you guys. So what information do you still need? The limits of integration. So that's going to be when y is equal to 0. So that's going to be at x equals 0 or x equals what?
2.
2, right? Because inside that square root is 4 minus x squared, which would give you 2 or negative 2, but it's in the first quadrant, they said, right? So that's going to be x equals 2. So now you have your limits of integration, 0 and 2, and you're looking for the area, and they give you c is equal to 6. So y equals 6x times the square root of 4 minus x squared, and you're looking for the area in the first quadrant. So you know it's just going to be the integral from 0 to 2 of 6x root 4 minus x squared. So let's go ahead and do that because we don't have our calculator now, right? So we have to do that by hand. So again, this is 0. That's 2. And we have y equals 6x root 4 minus x squared. So the area for part A, the area is equal to the integral from 0 to 2. I'd maybe pull out the 6 and have x root 4 minus x squared dx. If you had to integrate that by hand, what would you do? Use substitution. So u equals 4 minus x squared. du equals negative 2x dx. dx equals du over negative 2x. So this ends up being 6 times the integral. Because we did a u substitution with a definite integral, I'm going to change my limits of integration, right? And this is going to end up being x times root u times du over negative 2x. That x cancels with that x there. So what are my new limits of integration? Well, if it was 0, what is it now? 4. And how did you get that, Emil? Yeah, you plug in whatever it was here as an x value, because this is, with respect to x, you plug that in here for x. So when x is 0, u is 4. Boom. Then when x was 2, I have that u is 0. So now I have this. Oh, look, my lower limit of integration is greater than my upper limit of integration. I need to flip my limits of integration and make the whole thing negative. But here's the thing. This is equal to, because of this negative 2 that's down there in the denominator, 6 divided by negative 2 is negative 3. So this is the same as negative 3 times the integral from 4 to 0 of root u, which I'll call u to the 1/2 du, which ends up being positive 3 times the integral from 0 to 4 of u to the 1/2 du, which ends up being 3 times antiderivative of u to the 1/2 is 2/3 times u to the 3/2, going from 0 to 4. Those cancel, and I have 2 times 4 to the 3/2 minus 0 to the 3/2, which is 2 times 8, which is 16. Right, 4 to the 3/2 is the square root of 4, which is 2, cubed, which is 8. So 2 times 8, which is 16. Okay. Now, they don't ask us for units of measure. But what would the units of measure be given the fact that both x and y are measured in inches? And I just found the area, square inches, right? So you might want to put 16 inches squared. Again, they don't necessarily ask for units of measure, so that wouldn't be required. Okay, for B, it is known that for y equals that dy dx equals that guy. For particular spinning toy, the radius of the largest cross-sectional circular slice is 1.2 inches. What is the value of C for this spinning toy? How would you approach that? So what type of so obviously, again, we haven't really talked about it going through, but you're always looking at like, okay, what type of problem do we have? So for part A, that was just area between two curves, which is really area bounded by one curve in the x-axis. There wasn't even a second curve. So the area bounded by, a curve. That was easy. For part B, for a particular spinning toy, the radius of the largest cross-sectional circular slice. When is the largest slice if you're rotating this about the x-axis? Right? You're rotating that about the x-axis. Where is the largest slice going to occur, guys? At the maximum of this function y. But look what they give us in part B. dy dx equals that thing. Right? dy dx equals c times quantity 4 minus 2x squared all over root 4 minus x squared. What am I going to do with that information in order to find information about the largest cross-sectional circular disc?
Set it equal to 0.
And what is that going to give me? When I set dy dx equal to 0, what does that give me, Lauren?
Like the critical points, or in this case, it would be like the relative maximum.
It's the x value where the max occurs, where the relative max occurs. It's the x value where the relative max occurs. Once you know that, then you could answer the rest of what they're asking for here, right? So for part B, I'm going to say dy dx equals 0 when what? The numerator equals 0 and the denominator does not. So that's really going to be 4 minus 2x squared equals 0, which is when negative 2x squared equals negative 4, x squared equals 2, x equals plus or minus root 2. It's not going to be the negative because I'm in the first quadrant, so x equals root 2. So what I'm saying is this max right here is going to be root 2, okay? Okay, now that I have that, that's when the cross-sectional circular disc is going to be optimized, or in this case, maximized. So now given that, see if you can figure out what we're looking for. For a particular spinning toy, the radius of the largest cross-sectional circular slice is 1.2 inches. So what I have here is for volumes of solids of revolutions using the disk method, remember how you find out what the, I take my super sharp samurai sword and I slice it and I get that and I show, and it's so the cross-sectional shape, right? The cross-sectional shape is this circle right there, and this is the radius, right? So now I know that, so the area is equal to just pi times r squared. And then what's always a question? Well, what is r, right? So r is equal to no, not 1.2. 1.2 is the area of the, oh yeah, it says the radius of the largest. Oh yeah, they give us, the radius is 1.2 inches. You're right, they do give us that, is 1.2. So, but no, that's of this one. In general, because r is changing. R is going to be 1.2 at that particular point, but r is changing. I want r to be in terms of x. So what is r? What is r? Oops, shoot. Let me choose my. So that is my r. So what is that? It's just going to be the y value, which is going to be c times x times root 4 minus x squared. right? So now that I have that, they say, okay, what about when R is 1.2 and it's the largest one? Well, if it's the largest cross-sectional disk, what's the X value, guys? We just figured that out. Root 2. And now they ask us to solve for C. So 1.2 equals C times root 2 times the square root of 4 minus 2, which is 2. So 1.2 equals C times 2. So C is 0.6. So we use the fact that R is equal to, in this case, just the Y value because of how, you know, we're just using the disk method. So R is just going to be the Y value, which they tell us is equal to 1.2. At the X value when this guy's maximum, the maximum. So we already figured out where was the maximum at X equals root 2 to get that. Let's see how Ask Mr. Calculus dealt with this guy. Here we go. Where are we at? 3. Okay, so part A got 16. Was this part B? Oh yeah, this was part B. So we have R, which is equal to Y, is a maximum when dy dx equals 0. That's at X equals root 2. So 1.2, which is the radius, is equal to the Y value, which they get C is equal to 0.6. So that's part B. Let's move on to part C for this one. Oops, let me go back here. Part C. It says, for another spinning toy, the volume is 2 pi cubic inches. What's the value of C for this spinning toy? So how would you do that? I'm going to put this. Man, I don't know where that ended up. Do you see that problem in here anywhere? Whatever. I'll just paste that. You know what I'm going to do also is I'm going to go back to this guy and I'm going to do the whole thing. Yeah, I'm going to do the whole thing. This will be better for me. Okay, so now going to this guy. For part C, if the volume is 2 pi, well, first of all, let's just find the volume of all of these guys. So the volume of the solid of revolution generated by revolving about the x-axis is just going to be the integral from 0 to 2 of a of x dx. So what's the area function, remember? A equals pi r squared, and r is equal to just the y value, which is cx root 4 minus x squared. So the volume is equal to, I'm going to bring out my pi. It's going to be the integral from 0 to 2 of r squared. So this ends up being cx root 4 minus x squared squared dx. And they tell us that the volume is 2 pi. So dividing both by pi, I get that the integral from 0 to 2 of, again, this ends up being c squared times x squared times 4 minus x squared dx has to be 2. Do you see that? Do you see what I'm doing? I'm applying this squared right here to this stuff, and I'm bringing the c, because that's just a constant, the c squared out. So then I'm going to have c squared times, inside here, this is just 4x squared minus x to the 4th, right? C times, so this ends up being 4/3 x cubed minus 1/5 x to the 5th going from 0 to 2 equals 2. Do you guys see where that's all coming from? You with me? Are you guys with me? They're with me. Derek's with me. So I have c squared times. And I did that on purpose. I left it completely nasty and unsimplified on purpose. Now, how did Mr. Groller, when you take the square root of both sides, you got to add a plus or minus? Yeah, typically you do, but here they told me that c is a positive constant. So I didn't need to put the negative in there. Wait, can I just leave it like that, unsimplified? Yes. Totally. Let me actually see if he left it like that. Look at that. Boom. He even left it and boxed it unsimplified. You shouldn't simplify for your answers on the FRQ. Because all that you could do is make a mistake and make it wrong when it was right, but you'll never get more points for simplifying. So leave it unsimplified. We are totally cool with that. We are testing you on whether you know the calculus, not whether you know the, how to simplify, within a radical or anything like that. Okay. So I left that unsimplified on purpose to kind of prove a point. So far, so good. Now, check it, y'all. So far, we've been given these problems, and it started with the table of values. This was a, velocity vector and all that. So that was a velocity vector. And then this was a graph. So table of values, velocity vector. So you're given x prime of t and y prime of t, and now a graph. So 3 different problems, 3 different ways that they gave you the function or derivatives of the function. Here, again, they give us the graph. And they're saying, let f be a continuous function defined on the closed interval by blah, blah, blah. in between -4 and 6. We have 4 line segments here. And then it says, let g of x equal the integral from 0 to x of f of t dt. So g of x is what I call the area so far function. And it's important to note, check this out, y'all. This is what I would do like right away. So I'm going to make this just a little bit smaller so I can see it all. And then I'll load up a little bit once I have it all copied down. So check this out. Here's what I would put right away. I would write this. I'd say g prime of x equals f of x. And I would put a box around that. That is an important thing to note. Do you all see that? That g prime of x is equal to f of x. So when I'm asked about, okay, on what open intervals is the graph of g concave up? G concave up. Sorry, hold on, I need to admit somebody. So what does G concave up mean? G concave up when what's true? When G double prime of x, which is equal to f prime of x, is positive. So it's tough for me to talk about G double prime of x, but when I'm looking at this as f prime of x and I'm given the graph of f there, on what intervals is f prime positive? That just means f is increasing. F increasing means that f prime is positive. And it does say open intervals. So this is true when, or from -4 to -2 union 2 to 6. Okay, part B. They're now throwing some other function in there, and they're calling it p of x. Let p be the function defined by p of x is equal to g of x times f of x. And then people say, oh my gosh, what? That's so hard. Find p prime of 3. Well, first of all, what's p prime of x? P prime of x is equal to the first times the derivative of the second plus the second times the derivative of the first. But again, okay, so let's find p prime of 3. P prime of 3 equals g of 3 times f prime of 3 plus f of 3 times g prime of 3. So let's start with what's easiest for us to find. Is g of 3 easy to find? No, that's probably one of the tougher ones. So let's not do that yet. What about, because then I got, right, g of 3 using, you know, what g of x is equal to. I could say this, g of 3 equals the integral from 0 to 3 of f of t dt. So that's going to be this. So those two are going to be the same exact, right? They go up 4 and down 4. So those are the same exact areas. So it's just going to be this blue area in there. But that's, you know, a little bit tricky, I guess. It's 1, 2, 3.5. Anyway, I guess I'll just say equals 3.5. Okay, so P prime of 3. Yes, negative 3.5. Thank you very much, because it lies below the x-axis, so it's negative 3.5 times F prime of 3. F prime of 3 is the rate that F is changing at t equals 3. So what is that? 1. Plus F of 3. What's F of 3? Negative 3 times G prime of 3. What's G prime of 3? Well, look. G prime of 3 equals F of 3. So what is that again? Negative 3 again. So P prime of 3 equals negative 3.5 plus 9. So 5.5. Right? Okay, let's look at what we have going on so far for A and B based on Ask Mr. Calculus. This is number 4. Okay, that's what we have there. And they have 5.5 or 11.5. Okay. Now, oops, I have this whole thing on here. It says, we have a limit question. Oh no, a limit question. Find the limit. So for part C, find the limit as x approaches 2 of g of x over x squared minus 2x. Well, I plugged 2 in for g, and I see that the integral from 0 to 2, that's going to be 0 over 4 minus 4 is 0. So 0 over 0. So here's how you should write this, everybody. This is an important thing. Instead of putting equals 0 over 0, that's my little shortcut way of kind of showing you that it's L'Hopital's rule. On the AP exam, this is what I would want. Limit as x approaches 2 of g of x equals 0, and limit as x approaches 2 of x squared minus 2x equals 0. So instead of putting 0 over 0, you would write it this way. Then you could say, therefore, by L'Hopital's rule, this is equal to, or is equal to, by L'Hopital's rule, I guess I should say, is equal to the limit as x approaches 2 of g prime of x over 2x minus 2, which is equal to g prime of 2 over 2. So what's g prime of 2? G prime of x is just f of x. So I keep going back to this box, right? So what's f of 2? So I guess I could say that here, equals f of 2 over 2 equals, what's f of 2? Negative 4, right? Negative 4. So let's go to the solution and see what is said there. So they have the limit as x approaches 2 of g of x equals 0. In addition, the limit as x approaches 2 of the denominator is equal to 0. So by L'Hopital's rule, that is equal to that, which is equal to negative 2.
Just say LH right now.
Yeah, that's fine.
I still go to the hospitals and the test and didn't take up points.
No, that's how it's spelled.
Oh.
Look.
Yeah.
You know, but it's just pronounced L'Hopital. That's anyway. Okay.
I didn't actually know it's spelled the hospital. It's so, yeah, I love this FRQ.
Okay, I guess here we are. We have 5 minutes left. Let me just go through the last, couple problems. Part D, find the average rate of change on G, or of G. So that's going to be G of 2 minus G of -4 all over 2 minus -4. That's how you're going to start. And then, obviously G of, 2 is really, you're using this G of X function to find that. So that kind of guides you there. Anyway, I'm going to move on. So there's that. And of course, now that you know, ask Dr. Or ask Mr. Calculus, he can, or you can go through that. Okay, next. Let y equals f of x be the particular solution to the differential equation. So, hey, we have a differential equation here. Is it separable? Is this separable? Yes, it is. It is, right? Awesome. Write a second degree Taylor polynomial. Okay? In general, second degree Taylor polynomial. So let me just write this here. Second degree Taylor polynomial, always. So second degree so T sub 2 of x is equal to f of c. Did we use c or a? I forget. Okay, f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared. Always. Because even more general, the nth degree is t sub n of x, which is f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus f triple prime of c over 3 factorial times x minus c cubed plus dot 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 plus the nth derivative of f at c over n factorial times x minus c to the n. In general, that is what the nth degree Taylor polynomial looks like, right? So it's just that pattern. So like make that flashcard to know what that looks like. But here we're stopping at 2. Stop at n equals 2, and that stops you here. Anyway, going back to that problem, write that. Use Euler's method. Remember Euler's method, right? You have your different columns. You have n, x sub n, y sub n, and dy dx evaluated at x sub n, y sub n. And you know that the next y value is equal to the previous y value plus the derivative at the previous y value times the step size. And then you go through, right? We have done that recently, so hopefully that's still somewhat fresh in your mind. And then it says, and by the way, part C is going to be worth the most points. Find the particular solution with that initial condition. That's just going to be using separable differential equations. Separate out the variables, right? So that's not bad at all. Okay, and then the last one is something about a Maclaurin series, right? And we're not surprised to see that. The function g has derivatives of all orders for all real numbers. Maclaurin series for g is given by that. Do you notice that they say Maclaurin series and then we have x to the n? So of course it's centered at 0 because it's x minus c to the n, right? So state the conditions necessary to use the integral test. So now they're not even referencing this. They're going to something else. They give you this information that's general that you're going to use eventually for problem 6. But then in part A, it says, State the conditions necessary to use the integral test. What are the conditions? In order to use the integral test, what needs to be true?
It must be positive, decreasing, and continuous.
It must be continuous, positive, decreasing function. Is 1 over e to the n positive? Yes. Is it continuous? Yes. Is it decreasing? Yes. Boom. Integral test. Right? Okay. Use the limit comparison test to show that the series g of 1, which is equal to that, converges absolutely. What does converge absolutely mean? Not only do we have that the series converges, but the series of the absolute value converges, right? So for that one, you would just get rid of that alternating part, meaning take the absolute value of all of that. Anyway, determine the radius of convergence. What do we use to determine the radius of convergence?
Oh, the ratio.
Ratio test is used for interval or radius of convergence, right? The first two terms of the series g of 1 is equal to that thing are used to approximate g of 1. Use the alternating series error bound to determine the upper bound. All that you have to do, all that it says is, by going out to a certain number of terms, the error is bounded by the next term evaluated at that x value. So in this case, if you go out to 2 terms, that is accurate to within whatever the third term's value is. If the, I mean, I'll show you what he has here, but the error is just how to always write error. Absolute value of, the function minus whatever you're using to approximate the function. This is error. So in this case, what are we using? First 2 terms of g of 1. G of 1 is a Maclaurin series. So we say t sub. Now, I don't know what this n value is, but because first 2 terms, depending on what terms are 0 and all that, this might be t sub 2 of x. It might be t sub 1 of x. It might be t sub 3 of x. Whatever that is, this is error, is bounded by, and then this is going to be the next term. I don't know, because I don't know what the, watch. Let's go to, watch. From part B, we know that it converges, blah, blah, blah. The first 2 terms are used, and the alternating series error now will be the absolute value of the third term, which is when n is equal to 2. So the alternating series error bound is that when it's equal to 2.
In the one you wrote, though, would it be t of 3 of x?
Yes, if you are using t sub 2 of x, you would go out to the third term and then plug in the x value there, and then the error is within that for the alternating series error bound, which comes from the alternating series estimation theorem. That's where the alternating series error bound comes from. Okay, cool. I'm going to say, really, instead of me giving you, okay, do this for homework, in my Google Classroom, I've kind of put up there a bunch of those topics, the BC only topics that you can focus on. Focus on what you need to work on. If you are like feeling pretty good or you have enough time that you're able to do some of a bunch of those, then move on to the next multiple choice test, which would be, I believe, 3. I don't think you've done exam 3 yet in here, but just keep moving on in the review books for the multiple choice, or you go and you're looking at those problems, or on that YouTube channel, right, for the BC problems. Okay. All right, y'all. Great day, and I'll see you back here on Thursday, unless you have another AP exam. Bye, guys.